Hi everyone, I'm Emir. I am a senior electrical and electronics engineering student at 19 Mayıs University. In this video, I will talk about my 2-axis pan-tilt laser system that I control with a joystick. As you can see on the screen, when I move the joystick, the laser direction changes in 2 directions. Before we start, I wanna say I am still new to this. I'm not trying to act like an expert. I just wanna share what I learned while making this project. In this video, I will explain the parts I use, the wiring, the cubemic settings, and the basic idea of the code. Safety note, never point the laser at anyone's eyes. If you're ready, let's start with the components. I use the STM32F446RE as the main controller in this project. I used an Arduino Uno to provide a separate 5V power line for the servos. When I powered the servos directly from the STM32's 5V line, the voltage dropped because of the current draw and the system became unstable. Instead of an Arduino, you can also use a 5V adapter or a buck converter. All parts of the system share a common ground. LED status indicators. White LED shows that the system has power. It blinks 0.5 seconds on and 0.5 seconds off. Green LED turns on when servo moves up. Blue LED turns on when the servo moves down. Yellow LED turns on when the servo moves left. Red LED turns on when the servo moves right. 7-segment display shows the current servo mode, L for low mode, H for high mode, and S for sensitive mode. Buzzer BC547 NPN transistor. The buzzer makes a sound at startup and when the mode changes. I use BC547 transistor to switch the buzzer on and off. 16 resistors. I use these resistors to limit current for the LEDs and the 7-segment display. I use the KY008 as the laser source. SG19 continuous servo motor. In this project, I control speed and direction, not position. When I move the joystick, the servo rotates in one direction. When the joystick goes back to the center, the servo stops. So the joystick sends a speed direction command, not an angle command. 2-axis joystick module. It provides 2 analog outputs, VRX and VRI, for the control in 2 axes. 3x 1.5V battery pack. I used it to power the fan. DC motor plus fan. I used it for symbolic visual cooling in the system. Switch. I used it to turn the laser on and off manually.
Now we are at the connections part. The most important thing I learned is a breadboard is not always 100% reliable. Sometimes there is no contact, sometimes there is a wrong contact, and sometimes a part can be faulty. Because of this, I made a new habit. Before I put any part into the circuit, I test it one by one and I always read the datasheet. When you do this, finding problems becomes easier. and the risk of burning a component becomes much lower. Another important point is planning. Before you build the circuit, if you decide which part goes where and which pins I will use, you work faster and the pin selection becomes easier. Finally, wiring is really critical. It is very important to keep the wires tidy, group the wires that go to the same place, and fix them in place. Otherwise, even a small contact problem can become very hard to solve. Servos can draw high current, so I used a separate 5-volt power line and I connected all GNDs together. A soldered circuit is more stable than a breadboard, but for a prototype, a breadboard is faster. Now I will show the connections step by step on the screen using the images. White LEDs are set to blink to show that the system has power, 0.5 seconds on and 0.5 seconds off. I connected these LEDs to the PC2 and PC3 pins and carried the connections to the breadboard using 2 green jumper wires. In fact, using 2 separate pins is not strictly necessary. It is also possible to drive 2 LEDs from a single pin. However, in that case, it is more correct to use a separate series resistor for each LED. On the software side, I configured TIM6 to generate an interrupt every 500 milliseconds. At each interrupt, I toggle the PC2 and PC3 pins so both LEDs turn on and off at the same time. Because I planned the layout from the beginning, I placed the LEDs on the upper left side of the breadboard. I power each LED through a 220 to 270 ohm series resistor. The series resistor limits the LED current and protects the GPIO pin. I also cut the resistor legs so they are not unnecessarily long. This keeps the build cleaner and reduces the risk of poor contact or a short circuit. LED polarity is important. The long leg is the anode plus, and the short leg is the cathode minus. Direction LEDs are the LEDs I use to visually show which direction the laser is moving based on the joystick command. I drive each LED through a series resistor for current limiting. These resistors keep the LED current at a safe level and also protect the GPIO pins. I shorten the resistor legs to fit the layout so the build looks cleaner and the risk of loose contact or a short circuit is lower. I control these LEDs using the PB1, PB13, PB14, and PB15 pins, and I connected them to the breadboard with 4 jumper wires. I turn on the LEDs based on the sign of the command. If the x-axis command is positive or negative, the left or right LED turns on. If the y-axis command is positive or negative, the up or down LED turns on. When the joystick is in the center, all direction LEDs stay off. This mapping is done in the code inside the LED update from command function. First, I turn off all direction LEDs, and then I set only the LED that matches the command direction. I chose PB1, PB13, PB14, and PB15 because they are next to each other on the schematic, which makes the wiring more organized. One small note, if you check my older CubeMX file on GitHub, the LED assignment was different in the first design. In that version, the role and placement of the white-green LEDs were not the same. Later, I revised the project, so the current wiring and task assignment are exactly as I explain in this video. Before I explain the wiring of the switch, I will briefly describe how it works. In this project, I used an IC205 180-degree slide switch with 3 pins, SPDT. In this type of switch, the middle pin works as the common pin, COM. When the switch is in the left position, the middle pin is electrically connected to the left pin. When the switch is in the right position, the middle pin is electrically connected to the right pin. Based on this logic, I wired it as follows. I connected 5 volts to the right pin, GND to the left pin, and the S signal line coming from the laser module to the middle pin. In this way, depending on the switch position, the S line is pulled either to 5 volts to turn the laser on or to GND to turn it off. I use this switch as a hardware enable, so I can disable the laser instantly, independent from the software. For the mechanical setup, the switch did not fit firmly on the breadboard in a straight placement. To get a more stable contact, I placed the switch diagonally. Before I explain the wiring of the 7-segment display, I quickly checked the datasheet to understand how it works correctly. The model I used in this project is KPS 5161ASRND, and it is a common cathode type. In a common cathode display, all negative minus terminals of the segments are shared. You connect the common pin to GND, and you turn on a segment by sending a high signal from the GPIO. In a common anode type, it is the opposite. The common pin is connected to plus V, and segments turn on when you pull the segment line low. The display has a total of 10 pins. In the datasheet, there are 8 segment lines, A, B, D, E, F, G, and DP. These segment lines match the physical pins. When you read the pin diagram, it becomes clear which pin controls which segment. For example, pin 1 is segment E, pin 2 is segment D, and so on. In this model, pins 3 and 8 are the common cathode pins, so I connected both of them to GND. Instead of driving each segment line directly from the GPIO, I used a series resistor for each segment to limit the current. I shortened the resistor legs to fit the layout, which makes the wiring cleaner and reduces the risk of loose contact or a short circuit. After that, I routed the GPIO pins to the breadboard and connected each segment line to its assigned pin. In this project, I did not use the decimal point DP segment. I only drive the segments that are needed for the mode display. At system startup, the default mode is low, so the 7-segment display shows the letter L first. I also want to share an important problem I faced at this point. Even though all connections looked correct, some segments, especially the pin 1 segment E line and the pin 2 segment D line, would not turn on. When I tested the LED segments separately, they worked, but the problem continued when the same lines were connected on the breadboard. To isolate the issue, I first tested the segments one by one. Then I checked the jumper wires, the breadboard rows, and the connection points step by step. Finally, I realized the problem was not the display itself, but a poor connection on the breadboard line. As a solution, I moved these 2 lines to a different location on the breadboard to the same resistor node, and the problem was fully fixed. For this reason, with multi-pin components like a 7-segment display, if something looks logically correct but still does not work, it is important to always consider a breadboard contact issue as a possible cause. The laser module has 3 pins, S, signal, minus, GND, and the middle pin with no label is plus VCC. I wired it as follows. I connected the VCC plus pin to the 5 volts line and the GND minus pin to the common ground, GND. Even though I power the servos from a separate 5 volts line, I use a shared ground for the whole system, so I connected the laser module ground to the same common ground line. For the S signal pin, I connected it to the middle COM pin of the switch so I can control the laser independently from the software. This way, depending on the switch position, the S line is pulled to either 5 volts or GND, and the laser becomes active or inactive. The DC motor and fan part is quite simple. I connected the motor's positive plus terminal to the battery's positive plus terminal and the motor's negative minus terminal to the battery's negative minus terminal. Then I attached the fan propeller to the motor shaft and ran it. I powered the fan with a separate battery pack so it would not affect the power supply of the main control circuit. If you connect the polarity in reverse, the motor will spin in the opposite direction, and depending on the propeller direction, the airflow can also reverse. This part is not used for control. It is mainly included as a symbolic and visual detail in the system. The joystick module has 5 pins in total, GND, VCC, VRX, VRY, and SW. I connected the GND pin to the common ground. I connected the VCC pin to the 3.3 volts line because the STM32 ADC reference is 3.3 volts. This keeps the VRX and VRY analog outputs within the 3.3 volts range so the ADC can read them safely and accurately. Supplying the module with 3.3 volts also prevents the analog outputs from exceeding the ADC input limit, so it removes the need for an extra level shifter. I connected the VRX pin to the PA0 ADC input to read movement on the x-axis, and I connected the VRY pin to the PA1 ADC input to read movement on the y-axis. The SW pin is a digital button output that activates when you press the joystick. In this project, I did not use SW, so I did not connect it. For the buzzer connection, I used a BC547 transistor as a low side switch. In this setup, the transistor does the actual switching, and the STM32 only provides the on-off control signal. Low side means the switching element is placed on the ground negative side of the load, which is the buzzer in this case. I used a transistor instead of driving the buzzer directly from a GPIO pin, so the GPIO does not need to supply high current and the output is protected. The wiring is as follows. The buzzer's positive plus terminal is connected to the plus 5 volts line, and the buzzer's negative minus terminal is connected to the collector C of the BC547. The emitter E of the BC547 goes to GND. On the control side, I connected the STM32 GPIO output to the base B of the BC547 through a base resistor, about 1 kiloohms. I also added a pull-down resistor between the base and GND to prevent accidental turn-on. For example, 10 kiloohms, 47 to 100 kiloohms can also be used for a weaker pull-down. The pull-down resistor is especially useful during reset or boot when the GPIO may be floating because it prevents the transistor from turning on unintentionally. The operation is simple. When the GPIO is high, base current flows, the transistor turns on and the buzzer works. When the GPIO is low, the transistor turns off and the buzzer stays silent. In this project, I did not only use the buzzer as a simple on-off output. To create different alert sounds, I toggle the GPIO at different frequencies to generate tones, and I set the timing with microsecond level accuracy using DWT. In this project, I shared the general working principle, the hardware components, and the connection structure of the pan-tilt laser system controlled by a joystick. However, I did not explain the STM32 Cube MX settings and software codes in detail in this video because I do not yet consider myself sufficiently prepared to explain these topics properly. In order to avoid presenting the subject incompletely or incorrectly, I found it more appropriate to share the project files directly through my GitHub account for now, instead of explaining the code and configuration parts in the video. You can access the source codes and CubeMX configuration files of the project from my GitHub account. Therefore, I will end the video here.